On January 15, 2026, the Hubble Space Telescope turned its gaze toward an object that has captured the attention of astronomers worldwide. The target was 3I/Atlas, only the third confirmed interstellar visitor ever detected passing through our solar system. When the data came back, it confirmed something scientists had suspected but couldn't prove until now. This object is not round, it's not spherical like most comets, it's elongated, stretched out like a cosmic cigar, with a shape that makes it one of the most unusual objects we've ever observed. The measurements show a solid nucleus approximately 2.6 kilometers long, making it significantly larger than Oumuamua, the first interstellar visitor discovered in 2017, and roughly comparable in size to Halley's Comet. But unlike Halley's Comet, which formed in our solar system and follows a predictable orbit, 3I/Atlas came from somewhere else entirely, traveling through the void between stars for possibly millions of years before entering our cosmic neighborhood. The discovery of its elongated shape raises fascinating questions about how interstellar objects form, how they survive journeys across light years of empty space, and what they can teach us about planetary systems beyond our own. Some of the preliminary spectroscopic data from the James Webb Space Telescope has added another layer of intrigue, showing a chemical composition that differs from typical solar system comets in subtle but important ways. In this video, we'll explain what we actually know about 3I/Atlas based on real scientific observations, why its elongated shape matters, what the chemistry tells us about its origins, and what will happen when it reaches its closest approach to Jupiter in March 2026. Let's get started. To understand why 3I/Atlas is significant, we need to understand how rare interstellar visitors actually are and how recently we've been able to detect them at all. For most of human history, we assume that comets and asteroids were exclusively products of our own solar system, objects that formed 4.6 billion years ago from the same disk of gas and dust that created the sun and planets. That assumption went unchallenged until October 19, 2017, when astronomer Robert Weirich, using the Pan-STARRS telescope in Hawaii, discovered an object moving through the inner solar system at a speed that shouldn't be possible for anything gravitationally bound to the sun. The object, later named Oumuamua, was traveling at 26 kilometers per second relative to the sun, far too fast to be captured by solar gravity. Its trajectory was hyperbolic, meaning it would pass through the solar system once and never return. Oumuamua was the first confirmed interstellar object, and its discovery fundamentally changed our understanding of what moves through the space between stars. The object was gone before astronomers could study it properly, disappearing back into the darkness before detailed spectroscopy or high-resolution imaging could be performed. All we know about Oumuamua comes from a few weeks of observations as it receded from the sun, and those observations raised more questions than they answered. The object appeared to be elongated, perhaps 400 meters long, but only 40 meters wide, giving it a bizarre cigar-like or pancake-like shape depending on how you interpreted the light curve data. Even stranger, Oumuamua showed a slight acceleration as it left the inner solar system, a deviation from the trajectory predicted by gravity alone. Scientists debated whether this acceleration came from outgassing, like a comet releasing jets of gas and dust, or from some other mechanism entirely. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second confirmed interstellar visitor using a telescope he built himself. The object, named 2I/Borisov in his honor, was fundamentally different from Oumuamua. It looked and behaved exactly like a typical solar system comet, complete with a bright coma, the cloud of gas and dust surrounding the nucleus, and a visible tail stretching behind it as solar radiation pushed material away from the sun. Spectroscopic analysis showed that 2I/Borisov contained water ice, carbon monoxide, and organic compounds, a composition consistent with comets formed in the outer regions of planetary systems, where temperatures are cold enough for these volatile materials to freeze. The discovery of 2I/Borisov reassured astronomers that not all interstellar objects would be as mysterious as Oumuamua. Most would probably be recognizable as comets or asteroids, differing only in their origins beyond the solar system. But then came 3I/Atlas, and once again, the universe showed us that nothing about interstellar visitors is simple or predictable. The object was first detected on January 5, 2025, by the Asteroid Terrestrial Impact Lost Alert System, or ATLAS, a network of telescopes designed to scan the sky for potentially hazardous asteroids. Initial observations immediately flagged 3I/Atlas as unusual. Its trajectory showed a hyperbolic orbit, confirming it originated from outside the solar system, and it was approaching the Sun from a direction that suggested it came from the general vicinity of the constellation Sculptor, though tracing its exact origin is complicated by the vast distances and timescales involved. As astronomers continued tracking the object throughout 2025, it became clear that 3I/Atlas was neither a carbon copy of Oumuamua nor a twin of 2I/Borisov. It showed cometary activity, developing a coma and tail as it warmed up approaching the Sun, but the activity patterns didn't quite match standard cometary behavior. The coma appeared and disappeared in pulses rather than following a smooth curve. The brightness fluctuated in ways that suggested either an irregular shape, a rotating nucleus with varying surface properties, or possibly both. The January 2026 Hubble observations were designed to answer fundamental questions about 3I/Atlas that ground-based telescopes couldn't address. Specifically, what is the actual size and shape of the solid nucleus hidden inside the glowing coma? How fast is it rotating? And can we determine its composition with enough precision to compare it to solar system comets and other interstellar objects? Hubble's Wide Field Camera 3 was configured to observe the object using filters that minimize the contribution from the coma, allowing astronomers to isolate the light reflected directly from the solid nucleus. This technique, essentially digital subtraction of the surrounding gas and dust, revealed the shape that had been hidden beneath the bright haze. The nucleus is elongated with a length-to-width ratio of at least 2:1, meaning it's at least twice as long as it is wide. The absolute dimensions are approximately 2.6 kilometers along the long axis, though the exact width is harder to pin down because we're viewing the object from an angle that doesn't show us its full three-dimensional structure. For context, this makes 3I/Atlas significantly larger than Oumuamua, which was estimated to be only about 400 meters long, but smaller than 2I/Borisov, whose nucleus was estimated at roughly 1 kilometer in diameter. The elongated shape itself isn't necessarily strange. Many solar system comets have irregular, elongated shapes, particularly those that have experienced partial fragmentation or that formed from the gravitational collapse of loosely bound material. What makes 3I/Atlas interesting is the combination of its size, shape, rotation, and chemical composition, all of which together paint a picture that's still somewhat puzzling. The rotation data added another layer of complexity. During the brief observation window, astronomers measured changes in brightness that correspond to the nucleus rotating, presenting different surface areas to our view as it spins. The rotation period appears to be somewhere between 10 and 20 hours, though the exact number is still being refined. This is actually quite slow for an object of this size. Small asteroids and comet nuclei often spin much faster, completing rotations in just a few hours. The relatively slow rotation suggests that 3I/Atlas might be a fairly dense, gravitationally well-bound object, rather than a loosely aggregated rubble pile that would fly apart if it spun too quickly. The brightness variations also reveal something about the surface. The object doesn't simply get dimmer and brighter in a smooth sinusoidal pattern like you'd expect from a uniformly colored sphere or cylinder. Instead, the light curve shows sharper changes, suggesting that different parts of the surface have different reflectivity properties. Some areas might be covered in darker, carbon-rich material, while others expose brighter ice or possibly even different minerals. This patchwork surface is common on solar system comets, where ice sublimation constantly erodes the surface, exposing fresh material underneath and creating a mottled appearance. But in the case of 3I/Atlas, the pattern of bright and dark regions seems to be more extreme than usual, hinting that this object might have experienced unusual heating or processing during its journey through interstellar space. The spectroscopic analysis from the James Webb Space Telescope added crucial information about what 3I/Atlas is made of. And this is where things get genuinely interesting from a scientific perspective. Between December 2025 and January 2026, JWST observed the object using its near-infrared spectrograph, or NIR-SPEC, an instrument capable of detecting the chemical signatures of molecules and atoms in the coma and on the nucleus surface. The initial results showed the presence of water vapor, carbon dioxide, and carbon monoxide, all of which are completely expected for a comet and match what we see in both solar system comets and in 2I/Borisov. These molecules form when ice on the comet's surface absorbs heat from the sun and sublimates, transitioning directly from solid to gas. But JWST also detected spectral lines corresponding to metallic elements, specifically nickel and potentially small amounts of iron. Now, before this gets sensationalized, it's crucial to understand that metallic elements in comets are not unusual or mysterious. Every comet contains refractory materials, substances that don't easily vaporize, mixed in with the ice and organic compounds. These include silicate minerals, iron-nickel grains, and other rocky or metallic components left over from the protoplanetary disk where the comet formed. When cometary ice sublimates, it can carry these small dust grains with it, and those grains can be detected spectroscopically. What's interesting about 3I/Atlas is the ratio of nickel to iron appears to be higher than what we typically see in solar system comets. In most meteorites and cometary samples, iron vastly outnumbers nickel, usually at ratios of 10 to 1 or higher. But in the JWST data from 3I/Atlas, the nickel lines are prominent, while iron lines are weaker than expected. There are several natural explanations for this unusual nickel-to-iron ratio, none of which require invoking artificial objects or alien technology. First, the surface of 3I/Atlas might simply have a localized concentration of nickel-rich minerals, a pocket or vein of material that formed under specific conditions in the protoplanetary disk where the comet originated. Planetary formation is messy and heterogeneous. Different regions of a protoplanetary disk have different temperatures, pressures, and chemical compositions, leading to wide variations in what kinds of materials condense out of the gas. A comet that formed in a region with unusual chemical abundances might naturally have unusual metal ratios. Second, interstellar space is not empty. It contains extremely dilute gas, mostly hydrogen and helium, along with trace amounts of heavier elements, and it's constantly bathed in cosmic rays, high-energy particles that can alter surface chemistry over millions of years. A comet traveling through interstellar space for extended periods might accumulate a thin layer of processed material on its surface, enriched in certain elements that happen to be more abundant in the local interstellar medium. Third, and perhaps most importantly, spectroscopy of comets is notoriously difficult and subject to interpretation. The signals are weak, the coma creates a bright background that can obscure faint spectral lines, and different elements produce overlapping features that can be confused with each other. It's entirely possible that iron is present in normal abundances, but is simply harder to detect in this particular object because of viewing geometry, surface temperature, or other observational factors. What we can say with confidence is that 3I/Atlas shows a chemical signature that's slightly different from typical solar system comets, which is actually what we'd expect from an object that formed around a different star. Different stars have different elemental abundances depending on their age and the composition of the molecular cloud they formed from. A comet from a metal-rich system might naturally have more nickel or iron than one from a metal-poor system. The behavior of 3I/Atlas as it moved through the inner solar system also provided clues about its nature, and again, some of this behavior seems unusual at first glance, but can be explained through natural processes. One of the most striking observations was the rapid change in cometary activity between late December 2025 and mid-January 2026. For several weeks, the coma was bright and active, with clear spectroscopic signatures of water, carbon dioxide, and carbon monoxide being released from the nucleus. Then, quite abruptly over a period of about 12 days, the activity dropped dramatically. The coma faded, the gas production rates plummeted, and by late January, 3I/Atlas looked almost dormant, more like an asteroid than an active comet. This kind of rapid shutoff is unusual, but not unprecedented. Solar system comets occasionally show abrupt changes in activity, often caused by sudden changes in which part of the surface is illuminated by the sun. Comets rotate, and as they do, different regions of the surface move into and out of sunlight. If a comet has most of its ice concentrated on one hemisphere, you'd expect to see high activity when that hemisphere faces the sun and low activity when it rotates away. The 12-day timescale for the activity change in 3I/Atlas is actually consistent with roughly half a rotation period if the object rotates every 20 to 24 hours, exposing an ice-rich region, followed by an ice-poor or dormant region. Another possibility is that 3I/Atlas experienced a sudden mantle formation. Comets can develop a crust of non-volatile material, a mantle that insulates the ice underneath and chokes off sublimation. If a section of this mantle breaks away or cracks due to thermal stress, you get a burst of activity as fresh ice is exposed. When that exposed ice sublimates away and the mantle reforms, or the active area rotates out of sunlight, the activity drops again. The directional jet observations added another intriguing detail. Hubble detected a concentrated jet of material emanating from the nucleus, and interestingly, this jet appeared to be directed roughly toward the sun rather than away from it, which seems counterintuitive. Normally, cometary jets are driven by the sublimation of ice, and the gas escapes in whatever direction the local surface topography allows. The resulting momentum from the escaping gas creates a tiny thrust that can slightly alter the comet's trajectory, a phenomenon called non-gravitational acceleration. If the jet happens to be oriented toward the sun, it would create a force that pushes the comet in that direction. This doesn't mean the comet is steering itself or has thrusters. It simply means that the shape of the terrain where the ice is sublimating, perhaps a crater or a cliff face, happens to be oriented such that the gas escapes sunward. We've observed similar asymmetric jets on many solar system comets, and they're entirely natural consequences of irregular surface topography. The jets on 67P/Churyumov-Gerasimenko, studied in detail by the Rosetta mission, showed all kinds of unusual orientations, some pointing toward the sun, some perpendicular to it, depending on local surface features. What makes the 3I/Atlas jet interesting is that the non-gravitational acceleration it produces might be measurable, giving us information about the mass and density of the nucleus. If we can quantify how much the jet changes the comet's trajectory, we can work backward to estimate how massive the object is, and therefore whether it's a dense, solid body or a more loosely packed aggregate. All of these observations, the elongated shape, the unusual metal ratios, the rapid activity changes, the directional jet, need to be understood in the context of what we know about where interstellar objects come from and how they get here. Current models of planetary system formation predict that interstellar space should be full of ejected material, comets and asteroids and planetesimals that were gravitationally kicked out of their home systems during the chaotic early stages of planet formation. When giant planets like Jupiter or Saturn form, they scatter smaller objects in all directions. Some fall into the star, some settle into stable orbits, and some get flung outward at high speeds, escaping the star's gravity entirely and becoming interstellar wanderers. Our own solar system probably ejected trillions of comets this way, and every other planetary system likely did the same. The result is a vast population of orphaned objects drifting through the galaxy, moving at typical stellar velocities of tens of kilometers per second relative to the galactic reference frame. Occasionally, purely by chance, one of these objects will pass close enough to another star to be detectable. That's what happened with Oumuamua, 2I/Borisov, and now 3I/Atlas. Based on the detection rate so far, and accounting for observational biases, astronomers estimate there are probably thousands of interstellar objects passing through the inner solar system at any given time, but most are too faint or too far away to detect with current telescopes. The three we've found so far are likely just the tip of the iceberg, the brightest and most obvious examples of a much larger population. The fact that each of the three detected interstellar visitors has been different, Oumuamua, with its strange acceleration and lack of visible coma, 2I/Borisov, looking like a textbook comet, and 3I/Atlas, showing intermediate characteristics, tells us that planetary systems produce a wide variety of objects. This diversity makes sense. Different planetary systems form under different conditions. A system with multiple giant planets will scatter objects differently than a system with just one. A system rich in heavy elements will produce comets with different compositions than a metal-poor system. A system that experienced late-stage planetary migration, where planets moved inward or outward after formation, will eject objects with different velocity distributions and thermal histories. Every interstellar object we detect is essentially a sample from another planetary system, a tiny ambassador carrying information about a place we can never visit directly. 3I/Atlas, with its unusual shape and composition, might be telling us that its home system had chemical abundances or formation conditions significantly different from our own solar system. Or it might be showing us that comets can survive millions of years of interstellar travel and still retain enough ice and volatility to become active when they encounter another star. Either way, the object is teaching us something new. Looking ahead, the next major milestone for 3I/Atlas will be its closest approach to Jupiter on March 16, 2026. The comet will pass within Jupiter's sphere of gravitational influence, not close enough to be captured into orbit, but close enough that Jupiter's massive gravity will significantly alter its trajectory. This gravitational interaction is called a slingshot or gravity assist, and it will change both the speed and direction of 3I/Atlas as it exits the solar system. Astronomers will be watching this encounter closely for several reasons. First, the exact trajectory change will allow precise measurement of the comet's mass. By observing how much Jupiter's gravity deflects the comet, we can calculate the comet's gravitational pull and therefore its mass and density. This will tell us whether 3I/Atlas is a solid, dense object or a more porous, loosely bound pile of rubble. Second, the encounter might trigger new activity. As the comet swings past Jupiter, different parts of its surface will be illuminated by the sun at different angles, potentially exposing fresh ice that hasn't been active before. There's also a possibility, though small, that tidal forces from Jupiter could stress the nucleus enough to cause cracks or fractures, similar to what happened with comet Shoemaker-Levy 9 when it passed too close to Jupiter in 1992 and was torn into multiple fragments. 3I/Atlas won't get nearly that close, so catastrophic breakup is unlikely, but minor surface changes are possible. After the Jupiter encounter, 3I/Atlas will continue outward, eventually leaving the solar system forever and returning to interstellar space. Its trajectory will be slightly altered by the sun's gravity and by Jupiter's influence, but it will still be traveling fast enough to escape. Decades from now, it will cross the orbit of Neptune, then pass through the Kuiper Belt, the region of icy bodies beyond Neptune that includes Pluto. Centuries from now, it will reach the outer edge of the Oort cloud, the spherical shell of dormant comets that surrounds the sun at distances up to 100,000 astronomical units. And then, thousands of years from now, 3I/Atlas will enter true interstellar space once again, resuming its journey through the galaxy. Unlike Voyager 1, which will drift silently through space for millions of years as a dead artifact, 3I/Atlas will remain a natural object, potentially staying frozen and dormant until it encounters another star, millions or billions of years in the future. If that star has planets, if one of those planets has intelligent life, and if that civilization has developed astronomy, they might detect 3I/Atlas entering their solar system and wonder where it came from, just as we wonder now about where it originated. There's something poetic about that possibility, the idea that comets serve as messengers not just of information but of connection, silent travelers that link distant stars and distant civilizations across the immense voids of space and time. The scientific study of 3I/Atlas will continue throughout 2026 as the object remains bright enough to observe with major telescopes. Several research teams are planning follow-up observations with ground-based facilities and additional space telescope time. One of the key goals is to refine the rotation period and construct a detailed shape model showing not just that the object is elongated, but exactly how elongated and whether it has large-scale features like craters, ridges, or cliffs. Another goal is to monitor the activity patterns as the comet moves farther from the sun and cools down. Will the activity resume, or has 3I/Atlas entered a permanently dormant state? If activity resumes, does it follow predictable patterns based on solar heating, or does it show the same abrupt, pulsed behavior observed in January? Spectroscopic monitoring will also continue, tracking changes in composition as different parts of the surface are exposed and as various ice reservoirs are depleted. There's also interest in measuring the isotopic ratios of elements like hydrogen, carbon, and oxygen in the coma. Isotopes are variants of elements with different numbers of neutrons, and their ratios can reveal information about the temperature and chemical environment where the comet formed. If 3I/Atlas shows isotopic ratios significantly different from solar system comets, it would be strong evidence that it formed around a star with a different composition than our Sun. The broader implications of studying interstellar objects extend far beyond just understanding 3I/Atlas itself. Every interstellar visitor we detect and characterize adds to our knowledge of how planetary systems form and evolve. We're learning that planetary systems are not isolated islands, but are connected through the exchange of material. Over billions of years, the galaxy has become a vast mixing zone where objects ejected from one system can eventually enter another. This means that in principle, life itself could spread between stars if microorganisms can survive the long journey frozen inside comets. This idea, called panspermia, remains highly speculative, but the discovery that interstellar objects are common and that at least some of them retain volatiles and organic materials makes it less implausible than it once seemed. Even if life doesn't spread this way, the chemical building blocks of life certainly do. Comets carry water, organic molecules, and the raw materials for biochemistry. When interstellar comets enter a young planetary system, they deliver these materials to newly forming planets, potentially seeding them with the ingredients necessary for life to emerge. In that sense, every interstellar object is not just a relic of planetary formation, but a potential vector for the components of life itself. The technology required to study interstellar objects is advancing rapidly, and future missions will be able to do much more than we can today. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in 2025 and will survey the entire visible sky every few nights, detecting faint moving objects that current telescopes miss. Astronomers expect Rubin to discover dozens or even hundreds of interstellar visitors per year, transforming interstellar object science from the study of rare curiosities into a mature field with statistical samples. With enough detections, we'll be able to categorize interstellar objects, identifying common types and rare outliers, and we'll be able to estimate what fraction of planetary systems produce each type. There are also proposals for more ambitious missions. The Comet Interceptor, a European Space Agency mission scheduled to launch in 2029, will wait in space until a suitable long-period comet or interstellar object is discovered, then rapidly maneuver to intercept it and perform a close flyby with multiple probes. If an interstellar object is detected with enough advance warning, Comet Interceptor could potentially reach it and return images, spectra, and even dust samples from a visitor from another star. Even more ambitious are proposals for interstellar probe missions, spacecraft specifically designed to chase down and study interstellar objects in detail, returning data that ground-based telescopes simply cannot obtain. These missions remain in the conceptual stage, but the success of missions like Rosetta, which orbited Comet 67P for 2 years, shows that close-up comet studies are feasible, and extending that capability to interstellar visitors is technically possible with sufficient funding and political will. Right now, in early February 2026, 3I/Atlas is moving through the inner solar system at a speed of roughly 20 kilometers per second relative to the Sun, fast enough to cross the distance from Earth to the Moon in just 5 hours. It's currently located between the orbits of Earth and Mars, still visible through large amateur telescopes as a faint fuzzy patch, though it's nowhere near as dramatic as great comets like Hale-Bopp that dominate the night sky. Professional observatories are tracking it continuously, and every night brings new data, new measurements, new insights. Within 6 weeks, it will reach Jupiter and experience the gravitational slingshot that will determine its final trajectory out of the solar system. Within a year, it will have faded beyond the detection limits of most telescopes, becoming once again just another anonymous wanderer in the darkness between stars. But the data we've collected will remain, analyzed and reanalyzed for years, contributing to our growing understanding of what exists in the galaxy beyond our solar system's boundaries. This isn't science fiction or conspiracy theory, it's observational astronomy, the patient accumulation of evidence about objects that don't care whether we understand them or not. And every piece of evidence, every spectrum, every image, every careful measurement brings us closer to answering fundamental questions about where we came from, what else is out there, and whether our solar system is typical or unusual in the grand cosmic scheme. 3I/Atlas is just one object, a single data point in a population of trillions, but it's a data point we can actually observe and measure, and that makes it invaluable.